To understand why the industry is pivoting toward intensive biological systems, we must first examine the inherent bottlenecks of conventional activated sludge. In a standard CAS configuration, wastewater flows from primary treatment into an aeration basin, where suspended biomass oxidizes soluble organic carbon and converts ammonia into nitrate. The mixed liquor then flows into a secondary gravity clarifier, where biomass is separated from treated effluent through quiescent settling before being recycled back to the aeration basin or wasted. While reliable, this architecture is governed by physical settling velocity. The clarifier sizing is dictated not by hydraulic retention time, but by solids loading and surface overflow rates. Consequently, conventional activated sludge footprints are massive, leaving little room for plant expansion within urban footprints. Furthermore, system performance is acutely vulnerable to hydraulic surge events, temperature-driven changes in settling velocities, and filamentous bulking. When sludge volume indices rise, biomass washout compromises effluent quality. Operating at mixed liquor suspended solids concentrations typically constrained between 2,000 and 4,000 milligrams per liter, conventional activated sludge configurations cannot easily intensify volumetric loading without destabilizing secondary liquid-solid separation. Overcoming these physical barriers requires decoupling biological reaction from gravity clarification. The first major technological leap in decoupling biology from gravity settling is the membrane bioreactor. MBR technology replaces secondary clarifiers with microfiltration or ultrafiltration membranes, which can be configured as submerged hollow fiber cassettes or flat sheet modules integrated directly into the aeration basin or housed in dedicated membrane tanks. By utilizing physical barrier filtration with pore sizes ranging from 0.04 to 0.4 microns, MBRs achieve absolute solids retention, effectively eliminating effluent suspended solids and bacterial carryover. This absolute physical separation allows operators to maintain mixed liquor suspended solids concentrations between 8,000 and 12,000 milligrams per liter, 2 to 3 times higher than conventional systems. Consequently, hydraulic retention times are significantly compressed, and sludge retention times can be extended well beyond 30 days. This extended biological age fosters the enrichment of slow-growing nitrifying bacteria, ensuring robust nitrification even during cold weather operating conditions. Furthermore, the permeate is disinfected to a high degree, producing an effluent with biochemical oxygen demand and turbidity values consistently near analytical detection limits, ready for direct polishing or advanced water reuse applications. The coexistence of aerobic and anoxic zones within aerobic granules and advanced membrane bioreactor configurations facilitates simultaneous biological nutrient removal. In traditional nutrient removal configurations, such as the modified Ludzak-Ettinger or Bardenfaux processes, wastewater must pass through sequential anaerobic, anoxic, and aerobic tanks with extensive internal mixed liquor recycle pumps to achieve biological nitrogen removal via nitrification and denitrification. In contrast, advanced aerobic granular sludge and integrated membrane bioreactor systems accomplish simultaneous nitrification and denitrification within the same reactor volume or through tightly sequenced aeration cycles. Ammonia is oxidized to nitrate in the oxygen-rich outer layers of the granule or mixed liquor, and the resulting nitrate diffuses inward into the anoxic core, where it is reduced to nitrogen gas by denitrifying heterotrophs using internal carbon sources. Biological phosphorus removal is achieved by cycling phosphorus-accumulating organisms through alternating anaerobic feast and aerobic famine conditions, driving luxury phosphorus uptake and subsequent removal via waste-activated sludge extraction. This operational consolidation drastically reduces reactor volume, eliminates complex internal recycling pumping loops, and minimizes external carbon addition requirements.
Realizing the theoretical advantages of membrane bioreactor and aerobic granular sludge systems requires precise, automated process control. Unlike conventional activated sludge, which possesses significant hydraulic and biological buffering capacity, high-intensity systems operate at elevated organic and solids loadings, leaving little margin for operational error. The primary control variable in both technologies is dissolved oxygen management. In aerobic granular sludge systems, aeration intensity must be precisely modulated during specific cycle phases to maintain structural shear stress, which prevents granule fragmentation, while supplying sufficient oxygen for nitrification. In membrane bioreactor installations, aeration serves a dual purpose, providing biological respiration demand and supplying coarse bubble scouring air across the membrane surface to control boundary layer fouling. Automated dissolved oxygen trim valves, variable frequency drive blowers, and online oxidation reduction potential sensors are mandatory. Operators must continuously monitor sludge retention time, food to microorganism ratios, and effluent ammonia-nitrogen concentrations. Failure to maintain tight control over aeration cycles in aerobic granular can lead to granule deflocculation, while inadequate membrane scour in a membrane bioreactor leads to rapid, irreversible fouling. Every advanced wastewater technology introduces specific failure modes that engineers must mitigate during design and operation. In membrane bioreactor systems, membrane fouling remains the primary operational challenge. Fouling is driven by the accumulation of suspended solids, colloidal particles, soluble microbial products, and extracellular polymeric substances on or within the membrane pores. Left unchecked, transmembrane pressure rises rapidly, necessitating frequent physical backwashing, chemically enhanced backwashes, and rigorous clean-in-place procedures using sodium hypochlorite and citric acid. In aerobic granular sludge systems, the principal failure mode is granule disintegration or deflocculation. Excessive organic loading rates, high concentrations of monovalent cations relative to divalent calcium and magnesium ions, or prolonged starvation periods can destabilize the extracellular polymeric matrix holding the granule together. When granules break down into dispersed flocks, settling velocities plummet, sludge blankets expand, and biological nutrient removal efficiency collapses. Mitigating these failure modes requires robust pre-treatment, including fine screening and grit removal, along with strict control over influent chemical oxygen demand to nitrogen ratios and divalent cation dosing.
As we look across the wastewater treatment landscape of 2026, membrane bioreactors and aerobic granular sludge have proven that biological intensification is no longer experimental. It is the engineering standard for high-performance resource recovery facilities. By decoupling biomass retention from hydraulic settling and harnessing stratified microbial microenvironments, these systems achieve remarkable effluent quality within compact footprints. Yet, treating wastewater is only half the engineering equation. Managing the resulting sludge, capturing renewable energy, and recovering valuable nutrients represent the next frontier. In our next episode, we will explore the thermodynamics and microbiology of anaerobic digestion, biogas valorization, combined heat and power systems, and advanced biosolids management. Thank you for joining us on Water Atlas. Engineering a sustainable water future starts with precision science.